Hello everyone, good afternoon. Welcome to this class. Um, we are going to start straight by continuing from where we stopped in our last class. Like I say, I will always say, prepare your calculation sheet like this, right? This member reference. This is calculations. This is outputs. All right. Now, in our last class, we calculated and we were able to obtain our moment. Our movement was m equals to 10.314 times 10 raised to the power of 6 Newton millimeters. Then we now have our AS. AS required was 224.79 millimeters. AS we provided was 566 millimeter square. All right. Yeah, we provided this AS, which we have the reinforcement to be Y12 at 200 center to center bottom. Why did you say 200 center to center bottom? It's because we are designing for the span. And span reinforcement is at the bottom. All right. This is for the short span. But when you are designing for the long span, it's no longer, you will not call it bottom. Instead, you call it near bottom. All right. When you when you come across a design, you see bottom, it means that it's the shortest span. All right. The shortest span, the reinforcement is always at the bottom. Why the near bottom? You see end bottom. That is for the long span, the distribution. All right. Now, in our last class, we discovered that our AS provided was this. AS required was this. I said that I provided this because the steel they are producing in this country, they are also standard. All right. We're supposed to provide AS from this analysis, our calculation. We're supposed to provide 377 millimeter square, which is nearest to this in the table. This would have been Y12 at 300 center to center. But because of the substandard nature of the steel materials produced in this country, I cannot use this. That's why I'm now using Y12 at 200 center to center. All right. What we'll have to go straight to do now is to calculate for the service stress of the steel, FF, which is equal to 2/3 of Fy, characteristic strength of steel, multiplied by AS required over AS provided. All right. And we have AS required to be this. We have AS provided to be this. Okay. Where Fy is our characteristic strength of steel, which is taken to be 410 Newton millimeter square. And again, students will say no. What we normally use is 460. Yes, Fy is supposed to be 460. All right, 460 Newton per millimeter square. But again, the strength of steel in this country is not up to 460. We use 410. Even this 410 now, characteristic strength of steel now, if you go to the laboratory, you discover that it's even lesser than 410. So practically, we use 410. Okay. Now, this is equal to 2 over 3 multiplied by 410 multiplied by 224.79, that's AS required, over AS provided 566.66 millimeters. All right. So my calculator, when you compute this, it's 2 multiplied by 410 multiplied by 224.79 divided by 3 times 566. This one will give me, the answer of this will be equal to 108.56 millimeters square. Alright, how is that? You see, I'm cleaning this thing now because the board is not big enough to accommodate my calculations. But in your calculation sheet, all this calculation has to be inside your calculation column. Okay, now we move straight to modification factor. Modification factor is what? The formula for calculating your multiplication factor is 0.55, which is a constant, plus 477, a constant, minus service stress of steel, Fx, alright, over 120 constant into 0.9 constant, plus your moment over BD square, alright, BD square, where your BD is 1000 millimeters. This one is our D. Recall that in our last class, the D is equals to H, thickness of slab, minus concrete cover, which is 20, minus steel over 2. This one is 6 over 2. This one will give you 124. So that was how we were able to get this 124. So when you now input the values, you see that 0.55 plus 477 minus 108.6.56 over 120 into 0.9 plus our moment is 10.314 times 10 raised to the power 6 over 1000 times 124 square. This must be less than or equal to 2. Alright? If it is not less than 2, you use 2. If it is less than 2, you use the Lexar figure. Alright? So when you calculate this, you have calculating 0.55 plus 4 minus 477 minus 108.56. I have 368.44 over, complete the whole of this one. I have 0.9. Oh, that was 10.314 exponential 6 divided by 1000 times 124 square plus 0.9 times 120. This one is 188.49. Alright, this must be less than or equal to 2. Okay, when you compute this, you have 368.44 divide 188.49 goes to this plus 0.55. When you compute, total is modification factor is equal to 2.5 greater than 2. So you adopt 2. You use 2 for your modification factor. We are not done yet. Right? We are not done yet. These are the steps to follow. All these conditions must be met before you proceed. Now, we can clean. Alright, we can clean. What are we trying to get? We are trying to get check for the deflection. If whatever we are going to get at the end of the day is lesser than 124, it means the deflection is okay. All right. Now we now have D required. D required must be span effective depth ratio. Was the basic span effective depth ratio for me? I'm using 23 multiplied by what? Multiplied by multiplication factor. Now in our basic span effective ratio in the BS, the bill of quantity, in the BS code for cantilever, it's always 7. For simply supported slab, 26. For continuous slab is 20. But for us, let me check the code again to be sure. Of what I'm saying. Okay, I will correct that if it's wrong. So, but for me, this I'm using 23 because the slab continues in one direction only. So I'll update this. Then our span we worked on the span, the shortest span was the LX 4112.5 over 23 multiplied by 2. This must be less than 124. If you compute and it's less than 124, it means that the deflection is satisfied. Okay, when you compute this, you have when you compute that, please just don't mind me. When you compute this, we have 4112.5 divided by 23 times 2. This one will give me 89. This one will give me D required is equals to 89.4 millimeters, which is less than 124 millimeters. So because our depth slab we have been using is 124, and we have checked the depth required is supposed to be 89.4, means that the deflection is satisfied. All right. Now, in conclusion, in summary, I told you that we're going to prepare your calculation sheets. Prepare your calculation sheet like this. Calculation sheet, prepare like this. Here, which is less than 124. Here we see deflection. The deflection is okay. You can come here now. The output deflection okay. All right. Then after you have calculated for all your steel, the area of steel, now see AS provided. AS provided equals to 566 millimeters. That's where the Y, this is Y12 at 200 center to center bottom. All right. Then the AS required equals to 224.79 millimeters. All right. Now, these are the steps you follow when you're analyzing, calculating for your slab, the reinforcement to be used in your slab, in your beams, and whatnot. So, we have been able to solve for the mid-span movements. All right, we have checked for the deflection. Then we will now go back again to continue the same process designing the continuous edge for the short span or on the short span, right? Then before we now go back again to design for mid-span movement for the long span, then continuous edge for the short span. This is how you are going to work all your slab. Then you go to your beam, then you go to your column, then you go to your foundation. It's not easy. This is what we are trained for. This is what we are trained to do. But surprisingly, in this country, somebody that is not a professional will be handling a story building. It's an aberration. And that is why a lot of things are happening in this country. Building collapse here and there. So, having done all this, a client will not come and be telling you what to do. It's not done in a developed country. So, these are the steps to follow. For now, our deflection is okay. The reinforcement to be provided for this particular slab now in the shorter span is 12 mm reinforcement bar at 200 center to center spacing. Must be checked so that the building will be safe. Thank you. God bless. Now, next class, we'll continue from the continuous edge, all right, of this particular shorter span. Okay. For now, thank you and God bless.